2.6, related rates. So as I opened this up this morning, I kind of chuckled to myself because I was doing algebra with my 9th grade son last night, and he says something like, I don't ever want to do word problems again. And I laughed, right? Because that's actually the point of mathematics, is it allows us to make sense of problems in real life, okay? And so I told him, well, that's going to happen again. At some point, there's going to be more word problems. They're factoring right now, so they doesn't have any word problems, but they're coming back. So this section 2.6 and section 3.7 on Monday are both word problems, okay? They're going to be kind of intense, and they're going to be kind of involved. But they're applications of what we have done in a unique way, and that's why we're doing them here at the end. So some basic guidelines for solving word problems. A lot of times, we're going to end up making a simple sketch. We're going to set up equations relating the relevant quantities. For related rates and for optimization on Monday, we're going to be taking some derivatives. That's step 3. And we're going to do it implicitly. That was section 2.5 that for the most part you weren't super fond of. So we're going to revisit implicit differentiation on number 3. Number 4 is an algebra step where we're going to substitute values back in for known quantities. And then 5 is to solve for the remaining rate. Okay. I expect that you know some basic geometric formulas that I wouldn't give you. For example, on the test that you just took, I expected that you knew how to find the area of a triangle, right? But there are going to be some formulas that are going to pop up in the middle of this section, maybe in your homework or something like that, that you may have to go and do a real quick Google search and remind yourself, what's the formula of a cylinder or something like an area of a cylinder, or the volume of a cylinder or something. There may be something of that comes up. But anything that I test you on, either it will be a formula that you should know, it's pretty basic, or I'll give you the formula that you need. Fair? Okay. So this first one, we're going to read through the problem, and we're going to make that sketch that it's talking about. So a fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle of elevation theta between the line of the and the water changing when there's a total of 25 feet of line from the end of the rod to the water? If you're looking at this and saying, Dr. Hands, I don't fish, you don't need to. It's okay. The picture's going to set up into something that's very familiar. So the first thing it says is the fish is being reeled in at a rate of 1 foot per second from a point 10 feet above the water. So we're going to start with drawing something 10 feet above the water, okay? So I'm going to draw some water in just for our reference point. Here's my water. You can draw it flat if you wish. And I'm supposed to be 10 feet above the water. Okay? So right here is where I am fishing, and this piece is 10 feet, and it's not changing. Right? I'm constantly 10 feet above the water. So I'm in the boat, I'm on the dock, I'm wherever it is, I'm 10 feet above the water. That's a constant. Now, there is a fish. You throw the fishing line out, right, and the fish comes back in. So we're going to draw it, and I'll change colors. So right here is my fishing line, and it's out in the water. Now, as I reel the fish in, this line gets closer over here. Can everybody picture that? Right? The fish is moving in, so this fishing line is getting closer. I only want to draw one of them, but the image should be that that's changing. So this red line is changing. It's not staying constant. The 10 is constant, but the red fishing line is not. Everybody good? Okay, so that's a variable quantity, so we need to give it a variable name. I'm going to choose X. You can choose whatever you'd like. And this line coming back in, it tells us at the very beginning that it's changing at a rate of 1 foot per second. Right? So every second, it's 1 foot shorter. So it started at 25 feet out, then 1 second later, it's now 24 feet out, and then 1 second later, it's 23 feet out. Are you with me? The length of the line, as we pull it in, is becoming shorter over time. So this rate is called dx dt. Remember, the d's mean change. It's the change in x over time. Does that make sense? But that's also a derivative notation that we're familiar with. We don't use that one quite as frequently. We like to use x prime maybe, or y primes, right? But this is a derivative notation. And this is changing at a rate of 1 foot per second but it's decreasing, which means it's negative 1 foot per second. So in this picture, the only thing that's staying constant is the 10. This red line is changing. If I were to draw, and I'll draw it in now straight, my water, I'm going to make my water a straight line so that I have a better picture here. This blue line now for my water is also changing, right? As that red line comes in, this blue line's also getting shorter. The angles here are going to be changing as my triangle, that's the image I have, it changes. There's a lot of things changing. The 10's the only one that's staying constant. All good? Okay. It wants to know the angle of elevation between the line and the water. So either because you are familiar with the phrase angle of elevation, or because you have the picture drawn where you see the line and the water, this is the theta that it's talking about. Make sense? So there's usually a couple of clues, at least one, that tells you which angle it's talking about. So use the descriptions in there to get that piece. What you're trying to do then is you're trying to establish a relationship between the three things here that it's talking about. It's talking about how this angle is changing. I have a constant piece over here, and I have a rate here as well. And at some point it tells me that there is 25 feet of line that is out in the water. So there's going to be some point, not all the time because x changes, but at some point x is going to be 25. Okay, all good? I need to have some kind of a formula that relates the 10, the theta, and the x. What is it? Somebody be bold and give me a guess. You got it. Good job, Jackson. Thank you. It is sine of theta, and I'll write it exactly like you said at first, is opposite over hypotenuse. And in our picture, that's the sine of theta, is the opposite, which is going to stay consistent, that's my 10, over the hypotenuse, which generally speaking is x. Okay, all good? All right. What we do then is we take the derivative. I'm going to need this formula here in a minute. I'm going to copy it in another place too. Okay. I'm going to take the derivative of this formula. But the derivative is with respect to time. Okay? This is implicit differentiation. So first, what's the derivative of sine? Cosine. You got it. So it's cosine of theta, but it's with respect to time, so we put d theta dt afterwards. I actually think that this implicit differentiation is easier than the ones we did before. Number one, because the equations are going to be easier. And number two, because they're always going to say, every time you take the derivatives, you're going to use the variable and then dt. It's always going to say d theta dt, dx dt, dy dt, dr dt, whatever it is, it's going to have over dt. So you don't have to remember when to put it and when to not put it like you do with dy's and dx's. On the other side, I'll rewrite this. This is 10x to the negative 1. What's the derivative of 10x to the negative 1? Negative 10 x to the negative 2. And then that x is changing with time, dx dt. Okay, everybody good? So let's actually highlight the pieces of this that we know. We know dx dt. It's negative 1. Okay? It asks us to find the rate. Let me go back up there and highlight it. The rate for the angle of elevation. So it's wanting us to find d theta dt. So we don't know that one. That's going to be what we're going to be solving for. Right now, theta and x, I don't know. Correct? But at the specific point in time that it's asking me about it, I do know what x is. What's x? It's 25, right? So I actually do know x. I still don't know theta. Agreed? So how do I do it, Sophia? You solve for it. Over here, I have a relationship between theta and x, and I can figure out what theta needs to be. And your calculator will do all the work for you. So over here, I can come back and I can figure that piece out. So this is sine of theta equals 10 over 25. How do I solve for x when I have sine of theta? I'm sorry, how do I solve for theta when I have sine of theta on the left? Inverse sine, you got it. So we need to have the theta is equal to the inverse sine of 10 over 25. And when you do this in your calculator, I'd keep several decimals. Minimum of maybe 4. I probably would default to about 6 just to be safe. What do I have written down? I wrote down 4. So 4 to 6 decimal places at least. What is the inverse sine of 10 over 25? In radians. Make sure we're working in radians. I have 0.411517. Is that okay? Hit mode, and it should be highlighted on radians at the top. It probably is, unless you've been swapping calculators with somebody in like a trig class or something. All right, so at this point now, I also know theta. So I know every variable over here except d theta dt, right? So I can find d theta dt. So I have, and I can just write it in from where it is. I don't really need to solve yet, but this is the cosine of 0.411517. D theta dt equals negative 10 times 25. Well, I'll put 25 squared in the bottom. And then this is times negative 1. The only thing I don't know is d theta dt. So cosine on the left, I have too much work on my screen. I have 0.916515 d theta dt. My negatives are going to cancel, right? So I have 10 over 25 squared, 0.016, and then I'll divide to find d theta dt. And it'll tell you inside of WebAssign how many decimals it wants us to use. By default in class today, we're going to use 4 for no particular reason. Okay, we're just going to use 4. All right. So if I divide this, I believe I have 0.0175. That's the numerical value, but I do need units on it. What would the units be for that? So, yeah, say that louder, Jackson. It's radians per second. And if you're wondering how to think about that, you can actually look at this like you would a division, right? Theta is in radians, t's in seconds. So it's radians per second. Okay. So far, so good? Okay, our second one is a spherical balloon. So this would be an example of one that I probably wouldn't think that you just necessarily remember. And so I would give you a formula if you needed it. Let's read through it together. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 30 centimeters? So the first thing I'm going to do is to draw what? A sphere. So we're going to draw a sphere. So, oh my goodness, off screen. Here's my sphere. Something like that. And you can imagine this happening because you've blown up balloons before, or you've seen them blown up before. So it starts out really deflated, and then it increases, and it's telling you there's a certain rate of these things going on. So does anybody happen to remember the formula for the volume of a sphere?
4/3 I r squared.
Close. Cubed. Good job, Levi. It is 4/3 pi r cubed. If you don't remember, it's okay. I'd give you that, okay? That's actually a nicer formula than we had over here, because over here I had more pieces going on. I had theta and I had x, and it was just messier. It was messier in part because the theta was already embedded inside of a cosine, right? Or sine. We don't have that going on over here. It's just v. So when we take this derivative, the derivative is actually going to be an easier derivative to work with, just FYI. We have not written down all of our pieces yet in our picture, so I'm going to go back over here. Here's my radius, r. It tells us, again, at one specific point in time, the radius is 30, right? But it's changing in general. So r is a variable quantity, but at some point we're going to put in r is equal to 30. Does that make sense? Okay. And it also tells us one more piece of information. It tells us that the rate is increasing, there it is, by 800 cubic centimeters per minute. Is that the change of r or the change in v? That is a change in v. There's two ways you can think about that being the change in v. Number one is that r is a rate that it doesn't describe that. It doesn't talk about the radius changing, like in the language itself. It doesn't say the radius, right? Now, it doesn't actually say the volume either, but it doesn't say radius. The other thing that's sort of a red flag is it talks about cubic centimeters, right? Cubic centimeters are a volume quantity. Centimeters are a linear quantity. The radius is in centimeters. The volume's in cubic centimeters. So this piece of information right here that they give us is dV dt. So dV dt is 800 centimeters cubed per minute. And eventually we're going to use the r is 30 centimeters. Those are the pieces of information we have. So we're ready to do a derivative. So if we come over to our equation for volume, we take the derivative of the left-hand side, v, with respect to time. That is dV dt. Is that good? Always with respect to time. Now I need the derivative of the right-hand side, 4/3 pi r cubed. What's that? Don't overthink it. What is it? 4 pi r squared, which may be another formula you're familiar with. It may not, but that's actually the surface area of a sphere. There's a connection between those. We're not going to discuss it right now, but there is. So that's 4 pi r squared. But we also need dr dt. Every derivative we take is going to have the dr dt, the dx dt, the dy dt, the d theta dt, dv dt. It doesn't matter. There's going to have a related rates in place at differentiation. There's going to have a dt part to it, okay? But at this point, there's three variables, dv dt, which we know, r, which we know, and dr dt, which we're asked to find. So we have them all. There's no going back and trying to find theta like we did last time. That's very nice. So on the left-hand side, I have an 800. On the right-hand side, I have the 30 for the centimeters now. And dr dt is the only piece that I need to find. Feel free to simplify the right-hand side and then to divide it if you wish, or you can simply write it divided here now. That's the way I'm going to do it this time. So I have 800 over 4 pi times 300 squared, which is, or 30 squared, which is 900. Somebody find out for me, what does this give me with 4 decimals? Anyone have it yet? Yep, go ahead, Tanner.
0.0707.
Okay, and with 4 decimals, we'll stop there. Yeah, 0.0707. I need units. So again, we go back to what we're solving for, dr dt. What are my units on r? Centimeters. What are my units on time? T. What is it? This one's minutes. So this will be centimeters per minute. Okay, is that all right? Okay, the last one is the most interesting and the most maybe applicable, I guess, to some degree anyway. They all have application, but oil spills out of a tanker at a rate of 90 gallons per minute. Can you picture it happening? At least half of you guys are going to be engineers, right? Can you picture it happening? Okay. The oil spreads out in a circle with a thickness of 1/8 inches. What is a circle with thickness otherwise known as? A cylinder. It's a very, very shallow cylinder, right? But we've got a cylinder. And because there's viscosity inside of oil, there's the thickness that lasts, right? Whereas like if this were water, it would just deplete almost uniformly to completely the flatness of the ground, right? Right? Imagine like spilling water on the ground. It just sinks into the cement, right? Oil doesn't do that. So we're going to draw an exaggerated picture because otherwise we can't draw it very well. But it's a cylinder we're going to draw. So I'm going to draw a cylinder. And yes, I get to cheat. Copy paste is fantastic. Okay. Here's my cylinder. All good with my picture-ish? Okay. There's obviously a cylinder here, and I'm going to be working with the volume of the cylinder because it talks about determine the rate which the radius spill is increasing, and it talks about the volume of the way it's coming out, 90 gallons per minute, per minute. So I need the volume of a cylinder. Does anybody, again, this is one I'd give you, but does anybody happen to know or remember the volume of a cylinder?
Height times pi r squared.
Yeah, so the height, right? And then times the surface area of one of my surfaces, which is a circle, so that's the pi r squared. So height times pi r squared or pi r squared h. The thing that makes this a little bit trickier than the other ones is that it kind of looks like right now anyway that there's three variables, right? Radius, height, and volume. Yeah? So in some sense, it's kind of like the first problem we did, except that one of the pieces, right, the upright to the fishing rod was a constant 10. We're going to have that same sort of thing happening here. One of these pieces is going to end up being constant. So it's not going to end up being a variable quantity. All right, so let's get down some of the pieces that we have. We are told that the height is what? 1/8. This is the constant. So as the oil spreads out, it remains a constant 1/8. So the surface area changes, but not because the height is changing, right? It's changing because it's pouring out and spreading out, but still at a height of 1/8 inch. There's something else here that you need to be aware of. This was given to you in inches, correct? But something else was given to you in feet. So you have to make a decision. Do you want to work in feet or in inches? And there's not a right or wrong answer. It's a you pick. My notes are in feet. Can we go with feet? How would I turn 1/8 inch into feet? What do? Divide by 12, right? You have 1/8 of an inch, and you want it in feet. You divide by 12. So take your 1/8 inch, and let's figure out what that is in feet. What is 1/8 divided by 12? What is it? 1 over 96. Can you put it in a decimal for me? We'll just keep several decimals. It's just easier for me to put them in. 0.0104. Everybody good with that? That's my feet. The volume is interesting. So they actually tell us how the volume is changing. So dV/dt is in a weird unit that we're going to have to make amends for. And again, what would happen is that we would actually, I would give you this. This is gallons per minute. But I don't want it in gallons, right? That's not a linear kind of measurement that I can work with. So the one, let me find out where I put it. There it is. The unit that I would have to give you in order to do this problem is that 1 cubic foot is equal to 7.5 gallons. We need that because we need to change this dVdt into cubic feet per minute, much like the last problem was in cubic centimeters, right? I need this in a cubic linear unit. That's feet. So the way that this happens is I take my 9 gallons per minute, and actually I'm going to show it to you like this. So I have 7.5, that's not a good 7.5 gallons is equal to 1 cubic foot. And I can figure out what I would have for my cubic feet. So I need 90 divided by 7.5. So 90 divided by 7.5 is what? 12. So this is 12 cubic feet per minute. And at some point, it tells us, not a rut, it's changing as we go, but at some point the radius is 100 feet. It's a big surface area, right? 100 feet out in the radius. It's a very large spill. Maybe not in the grand scheme of how spills are, but it is a large number. So I'm going to move this down here. Let's find the derivative here. So we're going to take the derivative, but the reality is that the height is a constant. So I'd actually really like to put the height of the 0.0104 in there to start with. I don't want to confuse things and think that I'm working with a variable there. So in a very real sense, I actually am going to take the derivative of this. Okay? So it's a constant. It can go up at the front with the pi if you'd wish. The v is dVdt. The pi and the 0.04, whatever, that piece right there would just stay. So pi and 0.0104. And then r would become 2r, so I'll put the 2 in the front. And then I have dr dt. Again, just like before, I have almost all these pieces. I have dv dt. I have r. So I can find dr dt. So dv dt in the the cubic feet per minute is 12. So 12 on the left. I have 2 pi times 0.0104 and r, which is 100, and then dr dt. So 2 pi times 0.0104 times 100. I have 12 on the left, and I have 6.5345 on the right that I will be dividing by. We're almost done. 1.868335, 8364. Some variation of that. We'll go with that. That's what my note says right now, if I've rounded a few places along the way. What are my units? This one is feet per minute. It's important for you to realize that if we had decided to do this in inches, the answer wouldn't be the same, correct? Because it would be in inches per minute instead of feet per minute. So what would I have to do if I wanted to turn this at this point into inches per minute? Multiply by 12. So if I multiply this by 12, I will get 22.0369 or thereabouts inches per minute. So if you don't want to work in the units that it wants you to give your answer in, you don't have to, but at some point you might have to make amends for the choice that you've made. All right, so reminder, there's WebAssign work and there's written work. The written work has 3 problems. I'm not sure about the WebAssign work, but the written work is where you're going to get the best feedback on this because WebAssign is going to be very hidden behind the scenes as to what's going on.